We just believe that we found a new acceleration for being all the way out there. Or new gravity, or whatever. Gravity now that you're way out in space instead of actually on Earth.
So I need an explanation of what I need to go back in time.
So we found out. We were trying to understand. This was our first conversation. Is that how does the satellite stand? Right. So obviously it can't be getting tugged in 9.1 back to the crust, right? Because otherwise it'd be submerging, there'd be other oceans hitting your house, just kind of fucking. So with that said, we're like, all right, let's find some more details that we need because we don't have massive satellite and such things like that. So we were looking and we found this local station. Sorry, Earth is the very same force that holds planets in orbit responsible for the formation of stars. So we're like, all right, let's use this formula. Okay. So we could use our gravity, we used Earth's radius, and we had what is it? I'm trying to remember what this is again. We found the average. We found the average mass of a satellite, right? Is that what it was?
No, we didn't need that. We had
this was the mass.
Using the mass of the Earth together.
Yeah, not the satellite.
Okay.
And then we recalculated with this because this is our radius of Earth. So we did our radius of Earth plus our distance to the satellite.
Right. Geostationary.
Yeah. So that's how we recalculated our new
Okay.
And then we threw that into the formula. We got the new acceleration. Which should be,
so this would be our new G, right? This would be
yes.
little G.
Yeah. So now we're trying to find. Our thought is if we find a formula for centripetal force, and we find the velocity, like the tangent velocity to it, that'll keep it staying in orbit. It'll just counteract that. So that'll be the answer that they asked at the very beginning, where they asked the orbital speed necessary to maintain geostationary orbit.
Okay. So I need a bit of a clarification of what you're going to do with this in relation to what you just said your plan was.
We just got that, so we were hoping that
Something would jump out at us.
Right.
We're hoping that there'd be an equation that would, like a centripetal force, like if the velocity was like velocity x with do we need theta for any of those from the other equations?
I don't think so. We can't. We don't know where it would be if we don't have time.
We're hoping centripetal force because the velocity going sideways with the acceleration, if we somehow got it balanced out, then it would continue to stay.
Well, okay, so what direction is this acceleration? Like you've got your picture there, draw it again. So that's the direction that the acceleration is going in?
Towards Earth, yeah.
Okay.
Yeah.
New gravity.
And what direction is the velocity going back?
Completely tangent to it.
Okay. So you mentioned several times centripetal force. Yeah. What is that?
It's actually not a real force.
Yeah.
All right, Pat. Explain further.
Well, first off, it's right there. I was waiting for that to pop. I knew that was your question that was coming, but I don't know. You just gotta find like whatever force, because it doesn't matter where it is. It's always gonna be going the same force, like tangent to it, you just gotta keep that distance the whole time. So I'm not sure if there's an equation we can find or set to equal. Really thinking that there was an equation. You have to balance it out. How else would they do that in real life? You know, with knowing how fast it needs to go. So there's gotta be an equation.
Well, so let's talk about the forces that are being applied to the satellite. What forces are being applied?
The new gravity.
So that's Newtonian gravitation, alright, just to clarify. So there's a difference between local gravity and Newtonian gravity. You guys know what the difference is?
Newtonian gravity, that's just the gravity between two masses, right? Okay.
What's local?
Well, it's like this square.
It's like when you're on the surface.
Right, so surface implies something, doesn't it?
I'm not really sure I'm taking a shot at it.
No, but like, alright, so it was a good shot because you said it was on the surface, right?
So like when you were like,
If it's on the surface, it's dependent on something. What is that dependence?
Distance.
Distance. Okay, so what distance?
Radius of the mass, the radius of Earth.
Well, so you guys just calculated an acceleration for something that was much further away from the Earth than something in the sky or something. And that the acceleration changed because of that. All right, so the variable that changed there was distance, wasn't it? Okay. So local gravity and Newtonian gravity are dependent on distance. If you're close to the Earth, you can use local gravity. So you can use the acceleration that you minus 9.8. If it's Newtonian, it means it's dependent on two objects between each other. So like it's a much further distance out, and it's usually dealing with planets or planets and moons and stuff. Okay, so that's what the difference there is. So all you guys have done so far is you've calculated what the acceleration due to on the satellite due to the Earth at this distance. Cool. So where do you go now?
We need to find our velocity.
So that's the end product. So there must be some sort of step in between. So I would encourage you to think about what forces are actually being applied to the satellite. Okay? That will be my talk to leave you with while I go elsewhere.
So we had the new gravity between the satellite to the Earth, right? So we took our force equals mass times acceleration, and we set it equal to the equation for that force between.
Because that was the only force acting on it. So
Yeah, that's-
it end up equaling the two.
Okay.
And then the masses canceled out. And then you knew A and you knew R, so you found B.
R was distance, and from there we just plugged it all in.
my only question
Finish it up.
about this is, that's the acceleration we found, it was going down, right? How did it find the velocity going up?
I think that's what that equation does.
That's what this equation is.
Yeah, same one.
Yeah, they're quite about the same. Alright, I gotta say, guys, you actually sold it to this in a very creative way.
That's what she said. It was not the way that
It's not the way most people try and solve this, alright? So, like, this is perfect. Good work. Can you think of another, what the other way might
I'm
be?
I bet I can.
Go on, tell me.
You could set.
it's kind of like
This equation right here, you set this equal to this.
which is what we did.
Yeah, but we could have done that right off the get-go and we could have solved for...
Wait, no, you couldn't. That's
Yeah.
not acceleration.
No,
So
No, that's...
basically what was the one with the two delta T?
Did anyone listen to what she said at all?
yeah.
You set this equal to this. You don't add our radius. You don't add right? So because we don't have our distance, but we can solve for time.
No, that was to find the radius
we know
from,
time.
that was to find the satellite to the center of the Earth. Because that's why she said don't add the radius.
Yeah, that's it.
Well, yeah, so there's a confusion there. Like,
You use this base equation. You don't use our added distance at the end, right? So we just use.
you use a form of that equation, but not the way you currently have it. So
Oh, make it R.
Make it
It's
either
little.
R or
G times M divided by A equals square root R. And then you can set that equal to that one, right?
again, that would be a creative way of doing it.
Wait, what are you asking?
All right. Well, let's talk.
Easier way to do this?
Oh, I'm not saying it's easy, because I actually think what you guys did was 2 quick steps. It was pretty straightforward. So let's talk about the forces. Maybe this will get to the point that I'm trying to make. So you've got your
And that's not a bad thing.
your Earth here, and you've got your satellite here. So what forces are acting on that satellite? Just gravity.
Like when they were,
So just gravity, right? Gravity goes into the center of the Earth, yeah? Alright, so what is the expression for gravity? Like what equation relates to that? No, that's net force.
No, it's
So you've got F grav equals minus G M1 M2 squared. We're going to forget about the unit factor for a minute, alright? Alright, so you've got this equation that describes the force in here, right? You've also got this equation which you have used very productively. What does that equation relate to?
This takes it hard, right? This takes for the gravity, right?
I don't disagree with you, but why can you use this?
Because you could switch, you could cross out the M1s, which are the mass of the actual objects, and then you just have the mass 2, which you know is the Earth.
Right, so I totally agree with you, but I actually, I need to know where this comes from. Where does this come from? Because you've used it. You would use it, you used it here, you would use it in this way. So where is it coming from? Right. So that equation relates specifically to uniform segregation. Alright? It describes, as you guys were talking about, the velocity when that you need in order to travel in uniform circular motion at a distance more from an origin point. So if you change the distance you are from the Earth, the velocity you need to travel in uniform circular motion will change also. The same thing with the mass. If you change the mass of the satellite, well then V or would have to change to compensate for that. Right? So you, like if you got a bigger mass, you would have to go further out in order to have the same velocity. Okay?
I think they actually
So that's where this equation is coming from.
is kind of isolated.
So in this method here, you can say this is equal to Fnet, which is what this is. Fnet in this case is mv squared over 1. Okay? So you can say minus g m1 m2 over or squared is equal to mv squared over 1. And as you rightly said, you can cancel one of the masses because it's the same mass. And so then you can just solve for v using this. Alright? Okay, so that would be the alternative. Do you guys understand what I'm doing there?
I feel like that method's a lot more complicated and like trying to like make sense of it all than the way we did it.
Well, I actually think it's deliberate that way because there's things that we want you to think about in relation to the forces that you may have bypassed by going through it. Because I have a load of questions about which I will begin. So do you guys all understand this? What I did here? Yeah.
How would we? Didn't you say there was a way we could do it if we didn't know R?
yeah,
That's what she was explaining. She was saying somehow we could cut out R
yeah.
if we didn't know the distance at all.
Oh, it was because we know that it rotates like the center.
Oh, that's what it was.
Oh, yeah. Yeah, no, you can't do that. So you just get the rotational or the angular momentum with the mass of the circumference of the Earth.
And that would give you the
That would give you.
They explain the plot though.
That would give you the
radius.
That would give you the velocity.
He's just in the trailer. He's just a character.
Wait, she said that was for like finding the radius.
Yeah, that's finding.
That's to find out.
So V is equal to
It's not like cult information.
velocity of
Star Wars is
something moving in a circumference of omega or.
Also, Lucas has officially said these
So
is not
it's the same. So V over omega.
whoever dies.
So it's on the end. This is pi squared or something.
No, because